Hey there, everyone. In today's teaching session, I'm going to take you through a pretty comprehensive time series analysis for electricity demand forecasting. So why is this important? To be able to improve forecast accuracy, understand trend analytics, trend detection, seasonality. Are things cyclical? Are there patterns that we can exploit that we need to be aware of? Things like this. Optimize resource allocation, so demand planning and electricity grid management, cost reduction. Okay, we always have our eyes on finances, right? Either trying to make more money or trying to save money. In this case, we're trying to save money, so cost reduction. Enhanced reliability, right? We want to be able to make sure that the electricity grid is pretty robust, pretty scalable. It's able to meet customer demands, right? We don't want blackouts or brownouts. Strategic planning, any kind of infrastructure investing that needs to be done, any kind of short-term planning, long-term planning, we need to be aware of that. Grid balancing, right? So how do we balance the demand as it changes over time, right? In the summer months, there's going to be more demand for air conditioning. In the winter months, there's more demand for heat, right? And in the spring and the summer, at least in the northern hemisphere, it's kind of less of a demand, right? Because the weather is milder, right? We want to understand any kind of integration between renewables and dirty fuels or fossil fuels, which of course are oil and natural gas, fracking, things like this. Consumer insights, any kind of behavior analysis, that would be useful to understand any kind of demand surging, demand satisfaction. These would all be nice things to have. Any kind of regulatory compliance, reporting, compliance regulations, of course, economic efficiencies. Again, we want to have our eye on the finances and understand the impact of the bottom line, right? If we can save money, we're going to do it. If we can make more money, we're going to do that too, okay? So let's go ahead and import the required libraries here. These are the prerequisites, okay? We are going to be doing some scaling, ridge regression, forecasting, backtesting, one-hot encoding, and of course, time series analysis, right? So I have actually a few videos on time series analysis. One is univariate and multivariate time series analysis. So it's one variable and multiple variables analyzed simultaneously in the time series. And I have another video that loops through 7 time series models and then compares and contrasts the performance of each one relative to all the others. Okay, so take a look at those when you have a chance. So I'm going to go ahead and import the data. This comes from a GitHub repository, user content. The whole URL is here, so that's pretty obvious. And we're loading everything into a pandas data frame. We'll look at the head, which is by default the top 5 records, and the tail, which is the last 5. Okay, and if you put numbers in between the head and the tail, you can get that number of records displayed. If you wanted to see 100, for instance, we could do 100, and it's going to show us the top 100. Okay, I don't need that in this case, so I'll get rid of that. It's 5 by default. If you just want to see 1, you can see 1. Right? Anything in the parentheses, that is a parameter you can pass in and get whatever suits your needs, right? Okay, so for the first example here, I'm going to make sure that we have actual times here. Sometimes when you import data, it doesn't always come in the format that you expect it to. Time is not always time. Dates are not always dates. Strings or numbers are not always strings and numbers, right? So sometimes we have to format those or force it to be a specific data type that's going to be suitable for us. So we are going to do a quick check here for any missing values. I don't want to deal with missing values in this data set. It's pretty comprehensive. There's no missing values. If there were, you could backfill those, forward fill, use a mean. There's a bunch of different ways of handling missing values. I have a video on that. You can actually impute missing values using a couple different machine learning methodologies and get fantastic results. It can interpolate those for you if those are missing. In this case, we have no missing values, so that is good. One less step, one less headache, one less thing to deal with here. Now we are going to start doing some resampling and getting the means of these data points, right? And let's say a 1 hour interval. Okay, yeah, I want to look at 1 hour. So I used to work in the energy business. I worked in renewables, and this is exactly how we got the data in 1 hour increments throughout the year. So you'd have 1 a.m., 2 a.m., up to 22 hours, that's 10 p.m., 23 is 11 p.m., and 0 is midnight. Okay, so this is important so you can see the change in the demand for electricity over time. Now, at night, when most people are sleeping, the demand wanes, right? So it goes down, it's diminished, it's pretty much minimized overnight. But when people wake up in the morning, 7, 8, 9 o'clock, the demand spikes up as people are waking up, taking their showers, preparing breakfast, getting ready to go to work. They get to the office 9 o'clock, 10 o'clock a.m. Throughout the day, demand is pretty constant, kind of plateaus throughout the day, although there's variations, depends which market you're in. But in the evening time, around 5, 6 o'clock, there's still quite a demand. But 7, 8, 9 o'clock, you can see the demand is decreasing as people are starting to log off for the day, finishing up work, getting ready for bed, going to sleep. And then, of course, overnight, the demand is diminished once again. So this cycle repeats itself over and over. Monday through Friday is pretty consistent. Saturdays and Sundays, you'll see somewhat of the same pattern, but the weekends are slightly different, especially for office workers. People aren't going into the office. Saturdays and Sundays, they're at home, maybe traveling, maybe take a day trip, go hiking, go to the beach or whatever, go skiing if it's the winter time. So the demand on Saturdays and Sundays is different from Monday through Friday, right? So that's just something to be aware of. So that's why, anyways, that's why we parse everything into hours, okay? So I think that's enough about that. If we go down here, we're looking at a specific data set to test. We're going to get training and validation, okay, and copying out certain dates. So the data.lock is a location. iLock is locating the index, and location is just locating within the what's it called? Just the first feature here. The data feature is time. So lock is looking for the feature of time. If it's iLock, it's looking at the index, right? So two different ways of what's it called? Parsing data or identifying a specific data set, a subset of data that we're interested in working with. So we get the end training date. I'm sorry, the end train data, the end validation data, and then the data validation data test. This is important because we are parsing out different subsets of data, and we are going to plot this and see what the plot looks like over time. Okay, so I'm going to hit Control-Enter to refresh this. Okay, and I'm going to share all this code at the end of the video. I'm going to put this online when I post the video, and you will have access to all this data. So we don't have to really be paying too much attention to the nuances and all the details at this point. You're going to have all this code that you can download, and you can play around with it. You can explore the code. You can disassemble it, reassemble it, deconstruct it, and do whatever you want. So I'm going to share this with you. You don't have to take a lot of notes. Just pay attention to the main points of the video and the overall dialogue here and the purpose of what we're trying to do, right? We're trying to understand electricity demand and then forecast that demand. So if I plot this chart, we will see the update, we see the training, the validation, and the testing data, and we split this into different parts because we don't want the machine to learn everything. If it looks at the entire data set, it's just going to memorize everything. Okay, computers are great at memorizing things, but we won't know if it's able to generalize and make predictions on unseen records in a new data set. We want to see how accurately the model can learn, of course, but also how accurately the model can make predictions. That is a true test of whether or not the model was able to learn. Did it overlearn? Did it underlearn? Those are problems, right? If it's doing something like that, then we're going to have to add some hyperparameters. We're going to have to add some lasso or ridge regression, or use a different model, right? If it's learning too much and learning the nuances and the details of the noise in the data, that's going to be bad. But if it's not learning enough about the data, then it's underlearning, right? Can overlearn or underlearn, and that's bad too. We want to prevent both scenarios, and we want to be able to test the ability of the models to make predictions, right? Using some kind of metric like R-squared, mean square error, RMSE, something like that, right? So here we can see the training, validation, and test set. So this looks fine to me. Kind of choppy. Let's look at some more details. We are going to do grouping by demand and look at the median. This is the middle number. The mean would be the average. The median is the middle. and just try to understand what this looks like. So we have a box plot here, and we have the 12 months of the year. 1, 2, 3 is January, February, March. 11, 12 is November, December. Okay, right? So this is demand distribution by month, and you can see that the demand in January is slightly, well, we have some outliers in January. So we have some very cold days where the demand spikes over 9,000, but for the most part, it's around 4,000 to about 5,250. So February kind of has a broader deviation. It goes from about 4,000 to maybe 5,500. March kind of follows January, and so on and so forth. You see a little trend up in April, May, June, July. So this, I think, is more people in the Northern Hemisphere using the AC units. Kind of drops off in September, October, November, December. So heat, at least where I live, and I'm in New York City, and I've lived in several buildings, the heat is always cheaper than the AC. That's more expensive, okay? And I think the demand for energy and the physical properties to produce air conditioning, I think, is more demanding on the system. It's more taxing, so it's going to require more energy to pump out AC than to pump out heat. So I think that's why we're seeing this trend. So this is pretty interesting. I used to do this all the time when I worked in business, when I worked in the energy business, right? So this is pretty familiar to me. Let's look at seasonality by month. Let's look at weekly seasonality. So is there any pattern or trend based on the day of the week? Okay, so here we have the 7 days of the week. So you can see, let's see, Monday, Tuesday, Wednesday, pretty standard. Thursday dips down a little bit. Friday, Saturday, I'm sorry, Monday, Tuesday, Wednesday, Thursday, same. Friday dips down. Saturday, Sunday, different, right? That's what I mentioned a few minutes ago. So the weekend is always going to be slightly different. Demand is down. There's not so many people in the offices. People are probably traveling, just kicking back and relaxing. If the weather is nice, or outside, biking, hiking, running, whatever the case may be, right? But Monday through Thursday, demand's pretty consistent. Friday, probably people are working from home, and just slightly less demand in the office, right? But there will be some demand in people's houses, right? So we're not looking at such a granular level. We're just looking at energy demand based on the day of the week, okay? So that's intuitive. I think this makes a lot of sense. Now we're looking at days of the month, okay? So, I'm sorry, this is hour of the day, okay? Days of the month. This is hour of the day. So 1 a.m. until about 7 a.m. is pretty consistent. 8, 9, 10, jumps up a little bit, 11, 12, 13. So that's 1 p.m. 13 is 1 p.m. Then it kind of bounces a little bit. So you have 2, 3, 4, 5, 6 is 18, right? That's 6 p.m. drops down. So I think people are heading home from the office. Demand is decreasing steadily. People are probably fixing dinner at 19:20. That's 7, 8 p.m. Demand goes up a little bit, right? So 21, 22 spikes up a little bit. Maybe people reading, watching television, playing video games at home, something like that. So the demand is going up a little bit there, and then it stays steady around 11, 12 p.m. That's 23, 24. And this is the box plot again, like we saw in these previous charts. This is a pretty standard way to do that. I used to use these things all the time. But you can see the deviations spike. You see the upper and lower threshold. That's the, I think it's called the first and third quantile. And you see the lower threshold. So on number 1, you see the lower whisker, that's called a whisker, about 3,500, and the upper goes up to 8,000. So there are peaks and valleys here. So the minimum would be 3,500 kilowatts. That's what we're looking at here. And the maximum would be 8,000 kilowatts at 1 o'clock in the morning. So there was at least one instance of that. It might be two. It might be two circles kind of overlaid on each other. But that's kind of an isolated incident. That might have been, who knows what. I can't imagine. 1 o'clock in the morning, maybe some emergency, police, fire. Who knows? We don't have these kind of details about the data, but you can clearly see for most of the time, it's about 4,500 to 5,500 kilowatts at 1 o'clock in the morning. That's pretty consistent. So just good insight into the data, different patterns through the months of the year, days of the week, hours of the day, so on and so forth. So this is a violin plot, again, kind of similar to the box and whiskers plot that we saw before, where you show the extreme outliers, right? That's the tails, the left and right tail, and most of the fat distribution around the middle, where it kind of looks like a violin, the fat part of the violin, those are the most likely scenarios, right? But we do have a couple outliers that result on the holidays, right? And you can see holidays too seem to have their own pattern, right? So Christmas, Thanksgiving, what else? 4th of July, January 1st, New Year's Day. So the holidays, people are with their families. They're behaving and interacting differently than on a typical weekday, right? Or a non-holiday, right? So the distribution patterns are slightly different, and it's good to be aware of these things, right? So moving on now, we see autocorrelation and partial autocorrelation. Now, so this can show us relationships between demand and 1 hour and demand in previous hours. So is there some kind of correlation or some kind of overlap? If there's a high demand in 1 hour, is that going to spill into the next hour, right? And we can see that here. And this correlation indicates that autoregressive models can work pretty well. They can show us these lags in data, right? And we can see these obvious patterns in the demand for energy over a period of time, right? So there are definitely correlations and spillover effects. And you can see that if we go back to those box plots above, you can see there's a consistent pattern. I'm looking at the 24-hour bar chart now, box plot now, and there's a consistent pattern 1 to 7 a.m., right? Kind of jumps up a little bit, 7, 8, 9, 10, drops down a little bit. I think people are going out to lunch, entertaining clients, doing all kinds of variety of things. So the mornings are pretty consistent. Afternoon gets a little bit more erratic, and then we head into the evening and it's consistent again, right? So we see these autocorrelation patterns over and over. So that is not a huge surprise. That's actually what we would expect, okay? Let us look at forecast now. Let's do a forecast based on historical demand and see what this looks like. Okay. And then in the notes here I have, we can do backtesting, right? That's looking at something that's happened in the past and try to run an experiment on that and see if there's some kind of useful pattern of data that we can extract to make sense of into the future. Can we utilize this this knowledge that we have and this information that we've gained to make more informed decisions, more intelligent decisions about what demand will be into the future and how we can manage our business more efficiently, right? And backtesting is used to evaluate the accuracy and the effectiveness of models, and you can identify any potential issues, opportunities for improvement, process improvements, things like this. All right, so these types of tests are pretty interesting and pretty relevant too, right? So let me go ahead and refresh this. Control Enter to refresh the cell. And again, I'm going to share all this data with you, all the source code, so you'll have this at your fingertips. You can use it for whatever you want. I'm trying to make this pretty generic. I found this example online. I'll explain a little bit more about that later. But I'm trying to make this kind of customized to be able to do the experiments that we need to do to understand electricity demand, and then to be able to do forecasting once we understand the demand. But I'm trying to make this generic too, so you can apply this to your specific situation. So you might be doing your own electricity demand analysis, or you might be doing something related but slightly different. But I'm trying to make this whole process somewhat generic so you can copy and paste your data into this, or feed your data set into this, your data frame, or merge data frames if you have multiple sources of data. But make this run to solve your specific problems and answer your specific questions, right? So I'm answering some very specific questions here, but I'm trying to keep this general and somewhat ambiguous so you can take this data and adapt that pretty quickly and pretty easily for your own specific use case, right? So let's go down here and see what the training and validation shows us. Number of training periods was 24. So this is basically like looping through the data 24 times, and the TensorFlow world and PyTorch world, this is called an epoch. Otherwise, this is basically just a looping process, right? So we've done this process 24 times, and this is what we get. I'm going to plot this success all the time. Probably sick of hearing it by now, but a picture's worth 1,000 words, right? So if you go ahead and look at the data, that's all fine and well. If you plot it, And you can see that the real demand was in blue and the predicted demand was in orange. You can see how tightly these two lines match up. Right now, in the right-hand side, they kind of deviate a little bit between 22 and 29. This is the end of December, right? So this is probably all the days of December, the first through the end of the year. You can see at the beginning, the real demand and the predicted demand are pretty close, but something kind of caused it to get skewed a little bit and caused it to dislocate from the predicted values that were calculated were dislocated from the real values. So that's interesting, right? We're going to try to tighten that up and get that a little bit more crisp. Okay, so there we have the predicted and demand plot on top of each other. So let us do another forecast analysis using ForecasterAutoreg. Okay, so let me Control Enter to run this. We have 24 lags, and these are all hyperparameters that you can fill in, right? You can Google this stuff and you'll get a lot of information online. I had to Google it too to understand what it means. But then definitely show progress. This is a progress bar moving. We're returning the best job right here. Set this to true. Refit false. If we refit this, the model will take longer to run and to converge. We don't necessarily need to do that if we're getting good results initially. We have 24 steps, so 24 loops or epochs, they're called, right? And this is set to forecaster, and we're looking at the data frame, again, using the locator. And this is end of validation, right? From the data frame, we're getting end of validation, and we're looking at the demand feature. That's what this is. And then the metric is mean absolute error. I think this is pretty standard. There's a few that you can pick. Again, Google this, and you're going to find a lot of information in the documentation about this, okay? So this is running, 50% done. We can tell by the progress bar, 5 out of 10 epochs, and then the lags grid is going to have three epochs to finish that, right? Okay, so running, that's good, that's good. And then what do we have down here? The grid search results. Okay, so the search results appear down here. This is all the forecasted results from the analysis we did above, right? Because we don't know in the future what the demand is going to be. That's why we have to forecast it, right? We know historically what's been, and we can tell, okay, last year the demand was such and such in December, and the prior year it was so-and-so, and the year before that, we know that. So we can understand historically what it's been and make predictions into what it's going to be. That's a little bit more accurate. But if you didn't do all of these steps and you just ignore these exercises, you can still tell a lot from the historical data and use that to predict what's going to happen in the future. When I used to do this, I had 40 years of data, and you would see the same patterns show up again and again and again. It was very consistent year after year. Now with global warming, that could change into the future, right? Probably the winters aren't going to be as cold going forward as they have been in the past. So that is one huge reason that we need to do this forecasting, right? Like, we don't have this data going into the future about global warming. We simply don't. We have historical data where I used to work going back 40 years, and that's all well and good. But in the future, is that going to be accurate? It's probably not going to be too accurate too much longer with all the global warming that's going around, right? So the forecasting in this case is really imperative. Like, we really have to take this pretty serious, right? Because the historical just is not going to line up with what we're going to see in the future. Okay, so this thing is still chugging along. I'll admit it's taking a little bit longer than I thought, but I think it's almost done. We're getting there. And under the hood, it's doing a lot of work, right? It's comparing 30 models. It's doing forecasting, 24 steps for each iteration here. And then it's doing a parameter, grid search, lag grid search, looking at the end training data, the entire data set. So pretty robust analysis, right? So it is going to take a few minutes to converge here. So keeps on chugging. But I already know what the end result is going to be, because I ran this whole process just to test the code and make sure everything is going to work before I started the video. So let's just assume that finishes off. Let's continue down here with the analysis. We're about 2/3 done. We'll wrap it up pretty soon. So here's the metric to backtest the data. Again, we're doing forecasting. We're looking at demands, the number of steps, mean absolute error. That's a pretty standard way to do this. You could use a a few other metrics, right? It really depends on the scenario and what you're trying to achieve. Let us see what the result is now after doing the analysis. Okay, so this is pretty good. So now the predicted forecast is actually aligning with the real data pretty well. So the orange and the blue are lining up. Remember, before, when you get between days 22 and 29, there is a dislocation between the predicted and the real. Now these are lining up. After we retrained the model and got it a little tighter, a little crisper, this looks pretty good. So we're able to make pretty accurate forecasts now into the future, right? And again, we don't know what these are going to be, especially with global warming. That's a huge curveball. But with this type of analysis, what's happened in the past is good insight, but we don't have to rely only on that. We can make our forecasts into the future pretty robust and pretty accurate, right, based on these metrics that we see. So now we see a mean absolute error of 251.92. Okay, if I go ahead and Control Enter to refresh the cell, this should work. I did skip a couple steps, right? But this should work because I ran it just before starting the video, unless this is still running up here. We'll take a peek real quick. Could be. Yeah, it is. Okay. So it's still running, so I think we have to wait for that to refresh. But again, I know what the outcome is because I ran this just before kicking off the video here. So let's just go down. It's taking a little bit longer than I thought, I'll admit. So when we reran the backtest, we got 251 for the backtest error. So we went from 257 to 251. So that's a slight improvement, right? We ran the process, got a little bit tighter match there, but it's still off a little bit, right? So I think the first process is still running. I can tell because I see the hourglass in the upper left-hand corner of my notebook here. The Jupyter notebook indicates it's still running. That's fine. Let's just move on. We'll do another backtest, okay? So we had 257. We got down to 251. There's still some error. That's okay. It's a choppy data set. It's pretty big. There's going to be a few mistakes that the machine is going to make, right? It's not going to make a perfect forecast into the future. We can't expect that. There's going to be some issues. But the lower we can get that backtest error, the better it's going to be, right? So let's apply a couple more backtesting processes here to see if we can get that a little bit tighter. We got 257 down to 251. Now we're looking at the real and the predicted. So that is pretty tight. We've actually made improvement here between days 22 and 29 at the end of December. So it's looking better. I'm not going to refresh this. It tends to run a little bit slow. I'm not sure why. Predicted interval coverage is 75%. So we're covering 3/4 of the time span here. So that's good coverage. And then if we go down here, we'll see demand, temperature, holiday month. So we have a few different features now that we're feeding into the model, right? So we have a couple more features. Usually with these models, almost without exception, the more data you feed in, the better off that you're going to be. The model can learn more. It can learn the nuances, the details, all the ins and outs, ups and downs, back and forth of the data. So the more data you have, usually the better. Although you could have too much data if you have a high dimensionality data set. You might have to use PCA, LDA, some type of dimensionality reduction type of exercise to get the data down. But our data set was pretty sparse to begin with, so more features are better. We can do feature engineering and add new features into the data set to help the model to be able to train better and to make more accurate predictions. That's what we're doing at this point. So let us go down a little bit. Again, we see the plot, we see the tests and the predicted values. So kind of tight. We still see some deviations. We see some dislocations, but in a different way now, right? So the model is learning, but it seems to be making some new mistakes and fixing some old mistakes. So that's interesting. We'd have to do a few more exercises really to tighten this up a little bit. So now we got down to backtest error of 374. If I go up, I actually forgot what that was. 257 to 251. Okay, so it's actually not improving. It's actually making more mistakes at this point. So we're going to have to take a new approach to be able to predict our demand for energy at this point. And that's okay, right? We run these experiments because we don't know what the outcome is going to be. But if we're getting the backtest error lower and lower, we're going to keep going with it. If it's starting to flip and become higher backtest error, then we're going to have to try a brand new approach, right? This is starting to dislocate between the test value and the predicted value, and you can tell that the backtest error went from 251 up to 374, so it's actually kind of disintegrating a little bit here. That's okay. We'll just have to try a different approach. That's what these things are for, right? You try some different ideas, see what works, what doesn't work. Before you run it, you don't know what works, and what doesn't work, you have to test it and see for yourself, right? So let's see, we have almost at the end of this thing now. We have forecast autoregression, right? So a slightly different approach than we saw above, and we can go ahead and create and run this. I'm not going to run it because it tends to run a little bit slow now. I think the computer is just getting a little bit tired. It's late in the day. I'm getting tired too, so I can't blame the machine here, right? So if we go down a little bit, we have the regression outcomes here. This is ridge regression. So usually ridge and lasso regression could help you. It could add no value whatsoever. It could improve your ability of the model to learn and to make predictions, right? Because it is, especially if the model's tending to overfit and it's learning the nuances and the details of the noise in the data, that's bad. That's called overfitting. If it's underfitting, it's not learning enough details about the data and it's not able to make predictions. So overfit is learning too many details. You're actually learning noise that isn't important to the data, and underfitting, you're not learning enough, right? And you're not able to make predictions because the model can't learn enough. So ridge regression helps with overfitting of the model, right? And lasso regression does the same thing. So these are two techniques that you can apply to help the model to learn better and to, of course, make better predictions too. Okay, now we can see the test again. The tested energy demand and predicted are, again, kind of close, but again, they're dislocating too. So we're going to have to run a few more experiments and see if we can get this down. And the model is actually starting to disintegrate a little bit here because the backtest error now went up to 259. So I'm sorry, 359. So we went from a low of 250 up to 359. So that's okay. That's okay. It is what it is. We tried a few different ideas and we did predict pretty accurate forecasts, but definitely not perfect, right? So we'll have to continue with this process, run a few more tests. I'm not going to sit here and bore you with all the details, but there is a little more work that needs to be done. But we've already done some phenomenal things, right? We got pretty close forecasting of energy demand to match the actual demand. So we're pretty satisfied with that, and we can make some pretty accurate predictions. It still needs a little polishing here, but we did some pretty cool things. The last thing I'll say is this is not my own work. I found this example from this website. So let me copy and paste this. I'll put this in notes so you can check it out. I made a few changes here, nothing significant. I suppose like if I looked at the website and got a couple basic ideas and had some radical changes or significant improvements, I could call this my own work. This is not my own work, but I saw this online probably about 6 months ago, maybe 8, and I thought it was pretty interesting. So I wanted to discuss it on my blog here. So I'll show you the website. This is not mine, but I think this is great insight into energy demand forecasting. This guy did a really superb job with his analysis, right? So I'm not stealing it, not trying to take credit for this thing, but just highlighting what is available on this website. So take a look at that. So I think it's very interesting, very useful. Again, if you're trying to do any kind of demand forecasting, I think this is a great concept to follow. It takes you through like all the nuts and bolts, all the basics and pretty sophisticated things too. So it really covers the whole range from the simple to the complex. And I'm going to share all this code when I post the video later today. Okay, so again, copy paste it, run it in your own Jupyter Notebook environment, and take the code apart, put it back together, see how it works. I think it's a fantastic learning exercise. I think you'll definitely learn a couple new tricks once you get through this whole thing from the beginning to the end. So that's pretty much it. Hopefully this was enlightening and you guys learned a couple new things today. That's my objective here. That's my goal, to teach and to help people to get trained and to get up to speed on all kinds of topics pertaining to data science, machine learning, deep learning, business intelligence. I do optimization. I do all kinds of plotting and charting and gaining insights into data so you can make intelligent, informed decisions. Okay, so that's pretty much it. Thank you so much for your time today. I really appreciate that. And as always, have a wonderful day. Thank you. Goodbye.